Here I have a portable cable workout machine that generates electricity. This is a prototype where it's actually my 5th prototype so far, and this prototype actually charges and works for once. Here I have a multimeter that reads 1.4. This means how much voltage is inside the capacitor. This actually did work very recently. I got it to work an earlier iteration today, and now I've made a few small iterations of the design that makes it more sustainable. Of course, it's not perfect. For example, the gears unfortunately like to jump a lot, so I added this little push-in holder where I push down and it actually makes the gears mesh forcibly. And here is an attempt to try and make a desk mountable setup. This is my first attempt at making something mountable towards a desk, which was the goal, but again, I want to go towards a more wall mountable solution with open air suction cups, something like that. But overall, this is like a setup to see how this device works. So this power bank, essentially its input requires a certain amount of voltage and current, and when it passes through that and it meets its needs, this charge indicator will light up, indicating that this power bank is charging. Now notice when I plug this in, mind you, this reads 1.4 volts. This is the generated voltage left over from a previous experiment, but I'm going to plug it into the power bank. Notice how the charge indicator will not turn on, but the voltage here is dropping rapidly from the capacitor. That's because this power bank is absorbing the energy left in the capacitors, but the reason why the light won't turn on is because this charge does not meet the input voltage and current requirement to turn on the indicator. So now we're going to meet that requirement by pulling the cable of this machine, turning this human input into electrical energy that this power bank can have. Hopefully I can lift it up like this. Still experimenting here and there, so it's not perfect again, but this is just to show what I've been doing. Alright, ready, 1, 2, 3. As you can see, when I let go, it turns on, but if you look at the multimeter, it's reading a stable... Oh, oops. So you can see that number read 13.2 volts, and now the power bank is charging because it met a rapid voltage input and a large current input as well, which is why it turned on for much longer. So the reason why it didn't turn on during the strokes is because there was too much friction. The RPM was completely inconsistent. However, once I stopped, the voltage and current in the capacitors allowed the power bank to draw all that energy right back into it. So it actually did satisfy the need for voltage and current to be taken as an input. Because of that, the capacitor, even though it read 13.2 volts for a very short time, the power bank instantly swallowed all that energy up, which is why it's reading 1.1 volts, because again, it doesn't meet the requirement, so the power bank isn't as hungry to draw that energy back inside. So it's simply leaking into the power bank. Now, if I try again, this time, ready, 1, 2, 3. Paying attention to the multimeter. 4 point, 3 point. Looking at the power bank, it's not turning on at all. Of course, it turns on very briefly, time to time. Now let's give it a very hard stroke. All right, ready? 1, 2, 3, and 14 volts, and as you can see, the power bank was on for around 5 seconds. That energy is dropping rapidly, but the power bank's absorbing all of it, which is why it discharged so fast from the capacitor. Really rapid. It's just sucking all that energy up. And now, this power bank, for the past few hours of this video, I've been testing this multiple times to charge it up. This was at 20%. I tried to like discharge as much as I can. I have no idea how much it has left, but it's definitely gained a considerable amount of charge. If I plug it into this iPhone. Oh, oops, forgot. This is a charge. Oops. My bad. As you can see, it doesn't really replace a wall outlet. As you can see, it's 2 dots, so really didn't go up at all because it was like that before. But again, it's meant to be a more playful experiment, not meant to replace your wall outlets. Now, testing it out. There you go, it charges. Let's see if I can charge a phone. See if I can get the iPhone's indicator to pop up at least once. Just once. Looks like the hot glue's wearing off a little. Let's try to put this all the way up here. As you can see, voltage is still dropping, but it's not as rapid as before with the power bank, even at a lower state, because I guess in this case you could say is that the iPhone has a stronger circuit. Essentially, it prevents leakage. So now we're going to see if we can bypass its systems. See if I can generate just enough RPM to get a green light from the iPhone. Okay. Ready? 1, 2. Oh, oops. Oops. Okay. Okay. Nope. So the capacitor is draining extremely fast. However, even with the number reading 13.2 volts, the iPhone, as you can see, its charge indicator never turned on. So what that means is we probably went close to the required input charge requirement that the iPhone needs in order to charge smoothly, but we never made it in time. So yes, as you can see, it's discharging very, very quickly, but not as rapidly as the power bank 8 the remaining energy supply, because it did meet the requirements. So which is why this is being seen as standard, if you will. Let's try to plug it in back into the power bank. Alright, we're reading at 7.43. Plugging into the power bank, and 1, 2, 3, and you can see very quickly that the blue light flash. Okay, now it's just on. And it's draining extremely fast now. There you go. Yep.